Welcome to the deep dive. We've taken all the source material you sent over, and I mean everything from dense anatomy charts to the latest in exercise physiology, and we're here to turn it into a clear blueprint for knowledge.
And today's mission is a fascinating one.
It really is. We're going to try and understand the body's ultimate operating system by looking at it as a kind of, well, a self-regulating metropolis, a biocity.
And every single document you shared points to the one foundational law that governs this entire city.
Homeostasis.
Exactly.
Homeostasis.
Okay, so let's unpack that word right away because it sounds so rigid, like nothing ever changes. But that can't be right. That would be death.
Precisely. And that's the first huge insight here. The idea started back in the 19th century with Claude Bernard, who talked about the milieu intérieur.
The internal environment.
Right. He realized that for an organism to survive, it had to constantly buffer itself from the chaos of the outside world. Then Walter Cannon came along and coined the term homeostasis.
Which means staying similar, not staying the same. That's the key. It's a dynamic state of stability. Think of it as a relentless, constant adjustment.
So it's the body's coordinated effort to keep everything temperature, blood pressure, pH within this incredibly narrow, acceptable range.
And if those limits are breached for too long, the city fails.
So our mission for this deep dive is to map out the core systems of this biocity. We'll focus on the feedback mechanisms, the supply chains, and maybe most importantly, how it all adapts when things get stressful.
And that all starts with one dominant tool, the negative feedback loop.
The thermostat.
It's the body's thermostat, absolutely.
Yeah.
It's this self-correcting mechanism that runs almost every biological process you have.
I always think of it as having three simple jobs, and its whole purpose is to reverse any deviation from that ideal set point.
Right. Job one is just monitoring. You need a sensor or receptor nerve endings, chemical receptors that are just constantly checking the current value. It's the city surveillance system.
And that data then flows to job two, the control center.
Usually in the brain, like the hypothalamus. It compares the incoming data to the ideal set point and decides what to do.
And then job three is execution. The control center activates an effector.
Which is typically a muscle or a gland. And that effector causes a change that, and this is the important part, reverses the initial problem, bringing the system back towards that set point.
So if I go outside and it's freezing, my sensors tell my hypothalamus, which is the control center, hey, it's cold. And my hypothalamus tells my muscles, the effectors, to start shivering.
And that shivering generates heat, which reverses the drop in temperature. Simple, elegant, and incredibly efficient.
But here's where it gets really interesting. Sometimes the control center doesn't just try to hit the target. It deliberately changes the target itself.
You're talking about a fever.
Yeah, a fever, it seems like a total failure of stability. If your body is so dedicated to maintaining, say, 98.6 degrees, why on earth would it choose to raise its own temperature?
Because in that specific moment, survival is more important than stability. During an infection, you get these compounds called pyrogens circulating in your blood.
And they basically hack the system.
They hack the hypothalamus. They reset the homeostatic thermostat to a higher value. So now 101 degrees becomes the new target.
A temporary new normal.
Exactly. And it's still tightly regulated at that new, higher equilibrium. It's an adaptive strategy. That higher temperature makes it harder for bacteria to reproduce, and it actually boosts your immune cells.
So it proves the control center has the ultimate say. It can change the rules to win the war.
It has ultimate administrative power.
Okay, so if the control system is running things, it needs supplies. It needs a logistics network. Let's start with the circulatory system, the city's water tower and plumbing network.
And the main challenge here is managing volume and pressure. It has to deliver oxygen and nutrients to trillions of cells and then haul away all the waste like carbon dioxide.
At the center of it all is the heart, which isn't just one pump, it's a double pump.
A 4-chamber double pump. It's running 2 completely separate circuits at the same time. The right side is the pulmonary circuit.
Right, that gets all the used up, deoxygenated blood and sends it over to the lungs for a refresh.
And on the left side, the systemic circuit, which is much more powerful, gets that fresh oxygenated blood from the lungs and just launches it out through the aorta to the rest of the body.
And the vessels themselves are specialized, right? High pressure arteries go away from the heart, low pressure veins come back.
But if the arteries are the highways, the real action, the actual delivery, happens in the back alleys.
The capillaries.
The capillaries. They were the true exchange stations where the homeostatic transaction happens. Their structure is what makes the whole system work.
They're tiny, so thin that red blood cells have to go through in single file.
Right. And that maximizes the surface area and the time for oxygen to diffuse out to the tissues and for waste to be collected. The body's constantly micromanaging blood flow to these capillaries.
So it can dilate them in muscles you're using, but constrict them in, say, your digestive system if you're in a stressful situation.
That dynamic shunting of blood is homeostasis in action, and it works in perfect synergy with the respiratory system.
The city's air exchange facility.
Mhm.
Mm.
The gas exchange happens in millions of tiny air sacs in the lungs called alveoli. That's where blood meets air.
We always focus on getting oxygen in, but you argue in the sources that the more critical job, from a regulatory standpoint, is getting carbon dioxide out. Why is managing CO2 so important?
Because CO2 directly controls the acidity of your blood. When CO2 dissolves in water, it forms carbonic acid, and your body's pH range is incredibly strict.
So if it gets too acidic, everything starts to break down.
Enzymes, proteins, everything.
Mm.
So your breathing rate is often dictated less by a desperate need for oxygen and more by the immediate need to expel CO2 to stop the biocity from becoming toxic.
So when you're sprinting and your muscles are producing lactic acid, your breathing ramps up to blow off that CO2 and balance out the pH.
Almost instantly. It's the body's fastest way to correct pH, operating in seconds. It's a perfect partner to the kidneys, which are the long-term managers.
Okay, that makes sense. Let's move on to the precision regulators. The city's filtration plant, the urinary system, the kidneys. The numbers here are just mind-boggling.
They are truly astounding. The kidneys filter about 200 liters of fluid out of your blood every single day.
Wait, say that again? 200 liters.
200 liters. They use millions of these little microfilters called nephrons. Essentially, they clean your entire blood volume about 60 times a day.
And thankfully, we don't, excrete 200 liters of urine. That would be a problem.
And that's the precision part. After that massive filtration, the system performs a highly selective reabsorption. Nearly 99% of the water, the salts, the glucose all get pulled right back into the bloodstream.
So the real genius isn't in the removal, but in the careful retention of exactly what you need.
Exactly. And this is where the hormonal feedback loops really shine. Kidneys aren't just filters. They are powerful regulators of blood volume and pressure.
So if you're dehydrated, your blood volume drops.
Right. And the control center releases antidiuretic hormone, or ADH. It's like the city's water rationing manager. It tells the kidneys to stop releasing water and aggressively reabsorb it.
And what if blood pressure is low?
Then the kidneys activate something called the renin-angiotensin-aldosterone system. It's a mouthful, but
Not a critical one.
it is. It makes the kidneys retain sodium, and where sodium goes, water follows. So it raises both blood volume and blood pressure.
And then the opposite is true, too. If your blood pressure is too high, the heart itself sends a signal.
Yes, it releases natriuretic peptides, which basically tell the kidneys, hey, we've got too much volume. Get rid of this excess water and sodium right now.
It's a perfect negative feedback system.
Yeah.
Hormones to raise pressure and other hormones to lower it.
Beautifully balanced.
Okay, let's talk about the city's outer wall, the integumentary system, the skin.
It's doing triple duty. It's physical and chemical armor. You've got the tough keratin protein and acidic pH, and even antibacterial compounds like dermacidin. It's your first line of defense.
And it's also a massive sense organ. I mean, why invest so much in specialized receptors just to feel a light breeze?
Because that instant feedback is critical. Receptors like the Meissner corpuscle for light touch or the Pacinian corpuscle for vibration give immediate data to the nervous system.
So you can react before real damage occurs.
Exactly. And interestingly, as we age, cell turnover slows down, so wound healing takes longer. And we lose some sweat gland function, which is why older individuals often have trouble with extreme heat.
Right. And finally, the framework itself, the musculoskeletal system.
The structural roles are obvious. Bones provide shape, protection, the skull for the brain, the ribs for the heart and lungs, and bone marrow is the factory for all your blood cells.
But the deeper homeostatic role, the one we might overlook, is that bone is the body's largest mineral depot.
That's the key regulatory insight right there. Bone is the primary reservoir for calcium. And calcium balance is completely non-negotiable for nerve signals, for muscle contractions,
Including the heart.
especially the heart. If blood calcium drops even a little, the body will immediately start pulling calcium out of the bone matrix to restore the balance.
So your body will literally dissolve its own support structure to keep the nervous system online.
It absolutely will. The hierarchy of needs is very clear.
Wow. Okay, so we've established that the BioCity runs on these negative feedback loops to maintain stability. But what happens when the city faces a real crisis, an emergency?
That requires adaptation. And this is a higher order function of homeostatic control. The first response is immediate, and it comes from the nervous system.
The classic fight or flight.
The sympathetic branch, yes. Think about slamming on the brakes when a car pulls out in front of you. That instant rush.
That's the nervous system hijacking the whole city.
It is. The goal is to divert energy and max out logistics. Heart rate and blood pressure shoot up, breathing deepens, and the liver gets a signal to dump glucose into the blood for quick energy.
And at the same time, it's shutting down non-essential services like digestion.
Precisely. Now, this is a massive system-wide mobilization. You see a similar but more controlled version when you exercise. Hormones like growth hormone and cortisol go up, especially with intense resistance training.
But here's what's so fascinating. The difference between a single workout and long-term training.
Right. An acute bout of exercise elevates those stress hormones, but consistent prolonged training leads to an adaptive response called attenuation.
Which means the system learns not to overreact.
Exactly. With chronic training, your hormonal response to the same stressor is diminished. The body becomes more efficient. It doesn't need to sound the alarm quite so loudly next time.
You've basically trained your stress reactivity down. You've lowered your panic threshold.
That's a great way to put it. So structured exercise is really just a series of controlled stress tests. You're training your homeostatic systems to respond appropriately and, crucially, to return to baseline quickly.
And the danger then is when that stress becomes chronic, when the alarm is always on.
Yes. If the threat, physical or psychological, never goes away, those constantly elevated levels of cortisol and sympathetic activation can be devastating long-term.
Because you're always in emergency delivery mode. Constant high blood pressure leads to hypertension. The constant demand for blood sugar can exhaust the system and lead to things like type 2 diabetes.
The health of the BioCity isn't just about its ability to react. It's about its ability to successfully stand down.
So to wrap this all up, the fundamental success of this BioCity is really defined by its resilience.
It's all about resilience. The capacity to dynamically shift all these parameters to meet extreme demands, and then, just as importantly, to efficiently return everything back to that stable baseline range. Health is just the end result of all these systems working together smoothly.
We know the hypothalamic control center is so powerful it can deliberately reset your body's temperature to fight an infection. So that raises a really important question for you to think about based on the sources you provided. If your body can choose to raise its temperature set point to survive, how much of your long-term health is determined by the central nervous system's ability to choose, or maybe be trained, to actively return the set points of blood pressure and stress hormones back to those rest and digest settings after the crisis has passed?
A provocative thought. How much conscious control do we have over the resilience of our internal environment?
Thank you for sharing your source material with us for this deep dive. We hope you now feel informed and can appreciate the incredible self-regulating BioCity you live in every day.